Okay, let's walk through finding the expectation value of position for a harmonic oscillator in a specific state. So we are given a problem about a one-dimensional simple harmonic oscillator. You can see the Hamiltonian here on the slide. It's the standard one, h equals p squared over 2m plus 1/2 m omega squared x squared. Now the interesting part is the state the oscillator is in. It's not a simple energy eigenstate but rather a superposition. It's given by the state vector psi, which is 1 over the square root of 1 plus lambda squared multiplied by the sum of the first excited state ket1 and lambda times e to the power of I theta times the second excited state ket2. We are told that ket1 and ket2 are the normalized first and second excited states and lambda and theta are positive real constants. The question asks us to find the value of beta given that the expectation value of the position operator x in this state denoted by the expectation value of the position operator x in this state denoted by bra psi x ket t psi is equal to beta times the square root of h bar over m omega. We have a few options to choose from for the value of beta. Our approach to solving this is straightforward. We are given the state vector psi and the expected form of the expectation value of x. So our job is to actually calculate this expectation value using the properties of the harmonic oscillator states and operators. And then we'll compare our result to the given form to figure out what beta must be. Step 1 is to express the position operator x in terms of the more convenient creation and annihilation operators, A and A dagger. For a simple harmonic oscillator, the position operator x can be written as the square root of h bar over 2m omega, all multiplied by the sum of the annihilation operator, A, and the creation operator, A, dagger. This form is really helpful when working with the number states which are what ket1 and ket2 are. Let's review how the creation and annihilation operators act on the number states ket_n. The annihilation operator lowers the state by one level to ket_n-1 and introduces a factor of the square root of n. The creation operator, a dagger, raises the state to ket_n+1 and adds a factor of the square root of n+1. Now let's apply this to the states ket1 and ket2. Applying A to ket1 gives ket0 with a factor of the square root of 1. Applying a dagger to ket1 gives ket2 with a factor of the square root of 2. Applying A to ket2 yields ket1 with a factor of the square root of 2. And applying a dagger to ket2 results in ket3 with a factor of the square root of 3. Now in step 3 we use the expression for the position operator x from step 1 along with the operator actions we found in step 2 to see how x acts on our basis states ket1 and ket2. First, let's apply x to ket1. Recall from step 1 that x is proportional to the sum of the annihilation operator A and the creation operator A dagger. So we apply a plus a dagger to ket1. We distribute these operators and then use the results from step 2. A acting on ket1 gives ket0 and a dagger acting on ket1 gives root 2 times ket2. Combining these, we find the expression for x acting on ket1 shown here. Next, we apply x to ket2. Again, we are applying a plus a dagger to ket2. We distribute the operators and use the corresponding results from step 2. Acting on ket2 gives root 2 times ket1 and a dagger acting on ket2 gives root 3 times ket3. Substituting these into the expression gives us the final result for x acting on ket2 as shown here. Alright, in step 4 we calculate the result of the position operator x acting on a composite state vector ket psi. Due to the linearity of the x operator, it distributes over the sum within the state vector. We then substitute the results from step 3 where we calculated x acting on the basis states ket1 and ket2. The final expression for x ket psi is obtained by factoring out the common constant terms. Now for step 5 we calculate the expectation value bra psi x ket psi. First, we construct the bra vector from the given ket psi, which involves taking the complex conjugate of the coefficients as shown here. We then set up the calculation for the expectation value, taking the inner product of this bra vector with the result of x ket psi from the previous step. Notice how the normalization factors combine. Finally, we expand this inner product by distributing the terms as illustrated on the slide. Continuing with step 5, we use the crucial property of orthogonality for number states. Bra n ket m is 0 if n is not equal to m and 1 if n equals m. Applying this property term by term, most elements go to 0. We only keep the terms where the bra and ket states match. Putting together the surviving non-zero terms, we arrive at this expression. Finally, we factor out the common term lambda square root of 2 from the terms in the bracket. Continuing with step 5, we use the identity to replace the sum of exponentials with 2 times the cosine of theta. Substituting this into our expression, we then rearrange and simplify the terms. This involves carefully handling the square root terms. Notice that a square root of 2 term cancels out between the numerator and the denominator during this simplification. This leaves us with the simplified form. Finally, we rearrange the terms to match the target form for the expectation value of x. Now in step 6 we find beta. We were given that the expectation value is equal to beta times the square root of h bar over m omega. We calculated the expectation value to be 2 lambda cosine theta over 1 plus lambda squared times the square root of h bar over m omega. Comparing these two expressions side by side, it's clear that beta must be the coefficient multiplying the square root term. So beta is equal to 2 lambda cosine theta divided by 1 plus lambda cosine theta divided by 1 plus lambda cosine theta, and there you have it. The value of beta is 2 lambda cosine theta over 1 plus lambda squared. Looking back at the options given in the question, this corresponds to option number 3.